The laws of thermodynamics are postulates. That is, they are statements which we take on faith because we've never seen them to be violated. The first law simply states that energy is conserved. The second law is somewhat more complicated, and we will need a precise statement of this postulate so that we can build from this to develop the mathematical statements which will allow us to determine the direction of energy flow in systems. The precise statement of the second law of thermodynamics has three parts. The first part is there exists a state function called the entropy, S, such that for any real spontaneous adiabatic process, ds is greater than or equal to 0. This statement has several parts and essentially defines the entropy. The first thing to note about this is that the entropy is defined as a state function. That means that entropy can be associated with a state of the system, and each state of the system has a certain value of the entropy. The second important part of this definition is that it defines the spontaneous direction for a process. A process will be spontaneous if the entropy increases when the process is adiabatic. So this puts a restriction on the types of spontaneous processes for which the entropy increases. Recall that an adiabatic process is one in which no energy is transferred in or out of the system as heat. Let's consider a system that is not adiabatic. In other words, it can transfer energy to its surroundings. If we consider the surroundings as the universe, then the system plus surroundings has to be adiabatic because there is no place for the universe to transfer energy in or out of. The entropy of the system plus the entropy of the surroundings is denoted as the total entropy. So, ds total, since system plus surroundings is always adiabatic, ds total will always be greater than or equal to 0 for any real spontaneous process. And this is the statement of the second law that you are probably more familiar with. Delta S total is greater than or equal to 0 for any real spontaneous process. The second part of the precise statement of the second law gives us a way to calculate a change in entropy. This part of the statement says that for every real spontaneous process, we can imagine a reversible path such that ds equals dq reversible over t. First, this tells us that the equals sign in the first part of the statement of the second law holds when the path is reversible. So for any irreversible path, ds will always be greater than 0, but when we carry out a spontaneous adiabatic process under reversible conditions, that's when the equals sign holds. So we have to imagine a reversible path if we want to calculate the change in entropy. Notice because entropy is a state function, it doesn't matter whether we've done it reversibly or irreversibly, the change in entropy will always be equal to the reversible amount of heat transferred as divided by the temperature of the system. The last part of our statement puts these two parts together and states that for any adiabatic reversible spontaneous process, ds equals 0. Notice that if the process is adiabatic and reversible, dq will be 0, and therefore ds has to be 0.